Hello everyone, welcome to our video example that's going to be related to the lecture that we covered where we talked about non-ideal equations of state. In this case, this example is going to deal with using the generalized compressibility charts, how to read that, how to use the z-value into a problem. This is question 5.101 from page 272 from the textbook, so go ahead and read that question. I also have it repeated up here. So in this question, we have a gas mixture. We are given the composition of the gas mixture. We have 15 mole percent methane, 60% ethylene, and 25% ethane. It is compressed to a high pressure of 175 bar at 90 degrees C. So if you think about what's going on, now that we have very high pressures, the ideal gas assumption is probably not going to apply, so we need to use a non-ideal equation of state. This pressurized gas is going to flow through a process line, and we are given some specification. We don't want the velocity to be greater than 10 meters per second, so it cannot be too fast. What flow rate, so what's the amount kilomoles per minute, the molar flow rate of this mixture can be handled if we have the diameter of pipe as 2 centimeters. So first of all, what we need to do is to try to understand what are we given and what are we trying to find. We are given that the maximum velocity is 10 meters per second. We also know the diameter of the pipe, which means we know the maximum volumetric flow rate that can flow through this pipe. Because we know that volumetric flow rate is the velocity multiplied by the cross-sectional area of the pipe. So let's calculate what this volumetric flow rate, maximum volumetric flow rate allowable is. We're going to put in 10 meters per second. Area of the pipe will be pi d squared over 4. And so once we have that, all I'm doing down here is converting from meters cubed per second to meters cubed per minute. And now I have the maximum volumetric flow rate allowable in this pipe as 0.1885 meters cubed per minute. We want to know the molar flow rate, so kilomoles per minute. We have the volumetric flow rate. We need to convert between V to N, which means we need our specific molar volume, V hat. Because we cannot assume the ideal gas, we now need to use a non-ideal equation of state. We're going to do it using the compressibility factor equation of state. So we need to convert between Vmax to Nmax. We need the compressibility factor equation of state. And to calculate our Z, our compressibility factor, we first need to use K's rule because now we have different components. And that involves looking up the different temperatures and pressures, critical points, using table B1 of our 3 components, using K's rule to figure out the pseudo-critical temperature, pseudo-critical pressure. Using that, we know our operating temperature and pressure, calculate the pseudo-reduced temperatures and pressures. From that, look up the Z value, and then we can go on from there. So what I would like you to do now is to pause the video, fill in that table right there with the critical points, temperatures and pressures from table B1, try out K's rule on your own, and then once you get there, we can look at the Z value together. All right, welcome back. So hopefully you have a chance to try out this problem on your own. And first, looking up the table, you can get the table of values as you can see down here, the critical temperatures and critical pressures. The next thing to do using K's rule is just to weigh each critical value or critical temperature by the mole fraction. So the pseudo-critical temperature is just the mole fraction of methane, 0.15, multiplied by the critical temperature of methane, 190.7. Do it for the same with ethylene. For ethane, sum them all up, and you have your pseudo-critical temperature of 274.815 Kelvin. Do the same thing with your pseudo-critical pressure. So you're going to weigh each critical pressure by the mole fraction, and you end up with your pseudo-critical pressure. From there, I can find my pseudo-reduced temperatures and pressures by taking the operating temperature. In this case, it's 90 degrees Celsius, so I'm going to convert that to Kelvin. And I get a pseudo-reduced temperature of 1.32. Do the same with my pseudo-reduced pressure. Operating pressure was 175 bar, converted it to atmospheres, dividing by the pseudo-critical pressure that we found above, and you have 3.51. Now we can look up the generalized compressibility chart. If you look at the pseudo-reduced pressure we have is 3.51, that would be figure 5.4-3. That would be the appropriate chart to use. So here's the 5.4-3. We have a pseudo-reduced pressure of 3.51. I'm just going to take 3.5, so 3.5 right down here. We have a pseudo-reduced temperature of 1.32. So if you look through the lines, 1.3 is right here. This is the line for 1.3. This is the line for 1.4, so we're going to be somewhere within that range and then closer to 1.3. So since we have 1.32. So going up at 3.5, I actually gave myself a note right here. I put a point right here. It's slightly above the 1.3 line, not so much the 1.4 line. So we are right here, and then we're going to read across down here to get my z value down here, and that should be about 0.67. So we're going to estimate our z value as 0.67. How are we going to use this z value to calculate v hat? Let's go back to our definition of compressibility factor, which is PV hat over RT. We want to find our specific molar volume V hat, so we can calculate our V hat as ZRT over P. So just manipulating this equation. Putting in the numbers, again, making sure that your units are correct. I'm doing everything in SI, so that's why I'm converting my pressures to pascals, converting my temperatures to Kelvin. Put it all in, and I have my V hat. If I do everything in SI, I'm going to get it in SI units for specific molar volume. Volume per mole would be meters cubed, and then mole. So I have my specific molar volume down here. To convert from our volumetric flow rate to our molar flow rate, we can use this specific molar volume. You don't have to try to memorize this equation. Just remember V hat is V over N. So from there, you can just rearrange the equation. So N is just V dot over V hat. We have our V dot max from our first slide. We calculated what is the maximum volumetric flow rate we can have. Divide that by our V hat down here, and you end up with our maximum molar flow rate we can have, which is 1.63 kilomoles per minute. Now in this case, I kind of broke it up into two steps. First, finding the V hat, and then converting from V dot to N dot. You could also think about this compressibility factor from an ideal gas equation kind of manner. So think about this Z as a correction to the ideal gas equation. Ideal gas equation is PV equals to nRT. With this compressibility factor, all it is PV equals to ZnRT. So I could do it all in one step. If I do it all in one step, I rearrange PV equals to ZnRT for my N. I can do it as P times V over ZRT, and you'll get the same answer. All you're doing is combining the two steps that I shown down here. So that's all I have for this example as a practice to show you how we can use the compressibility charts and how we can use the Z value to eventually calculate our specific molar volume. Work hard, be smart. In the next lecture, we're going to start to put all these back together into our material balance problems.